Hello there and welcome to a brand new lesson. This is How Beyond Numbers, where we learn maths the easy way. In this lesson, we are looking at linear inequalities with two variables. By the end of this lesson, you should be able to represent a linear inequality in two variables as a region on the Cartesian plane. You should be able to draw the boundary lines, that is either the solid or the dashed one, correctly, or greater than or equal to, and then less than or equal to, or less than or greater than. You should be able to use the test points to determine which side of the boundary line to shade. You should be able to identify and describe the feasible region satisfying a given inequality. And finally, you'll be able to check whether specific coordinate points satisfy a given inequality. Now, as the lesson proceeds, here are some key vocabularies we'll be using. And I will advise you pause at this point and then quickly take a glance before we start the lesson. So without much ado, let's quickly look into it. So let's start by looking at what a linear inequality in two variables represents. When we talk of linear inequalities in our previous one, we work with what? One variable. This time we are moving to two variables. So we are not just looking at a single range of numbers that satisfy an inequality, but we are looking at a region altogether, specifically in this case, on the Cartesian plane that represents a range of possibilities. You see, so in other words, we are saying it doesn't just describe a line, such as what we did in our previous lesson, representing the inequalities on a number line, but then it describes an entire side of the Cartesian plane. In view of that, to get these regions that satisfy our inequalities that involves two variables, there are 5 steps we need to follow. So for now, I'll just quickly go through the steps. We look at the two lines and then we go straight into solving some questions that would enhance our understanding. So the first thing you need to do is you replace your inequality symbol with an equal sign. Remember, we said for inequalities, they always have what? A less than, a greater than, a less than or equal to, or a greater than or equal to. So you'd substitute or replace any of these with the equal to. And then you draw what we call the boundary line. So talking of boundary line, there are two types. You have the solid one. The solid line, when we say solid, we simply mean just a straight line like this, you see. Or the one that is dashed. So the dashed is just like this. You see, so you use the solid for greater than or equal to, or less than or equal to. That is to say, the points on the line also satisfy the inequality. And then we use the dashed for greater than or less than. Now, if you're able to get your boundary line, you choose a test point not on the line. Most often, if the origin, that is 0, 0, is not part of the boundary line, it is always easy to use it as your test point. Now, using it as your test point simply means you then substitute it into your inequality and then find whether or not that test point satisfies your inequality. If it does, then we are just going to shade all that portion as the region that satisfies our inequality. If it doesn't, then you just shade the other part. So with that said, let's answer some few questions to enhance our understanding. So our first question we have here says, describe how to graph y is less than 2x plus 3 and then state the type of line, which region to shade, and whether 1, 5 is in the region. It just says you should describe, but then I have my graph sheet here so that we actually illustrate it as well. So first of all, using the steps we laid out, if you want to graph this and then determine the region that satisfies, you need to set your boundary line. You see, so with the boundary line, what we said is you have to change your inequality sign and make it an equation. So that is to say, instead of our y is equal, instead of our y is less than 2x plus 3, we rewrite it as our boundary line, which then becomes y is equal to 2x plus what? 3. You see, then you draw this on your graph. Now, how do we draw this on our graph? We know that if you want to draw a line on a graph, you need at least 2 points. You see, and for those 2 points, that is your x-intercept and your y-intercept will be fine. See, so at x-intercept, the value of y is what? 0. So we say at y equals 0, it simply implies that we have 0, which is equal to 2x plus 3. Making x the subject, we have 2x equals negative 3. And our x is equal to a negative 3 over 2. You see, then we now find at x equals 0. So you say at x is equal to 0, then our y, it implies that our y is also equal to 2 into bracket 0 plus 3. And our y is equal to what? This gives us a 0, so we have 3. So this is to say that the points x is negative 3 over 2, 0. And then the other point, which is 0, 3, are on the line. So we come all the way to our graph and then look for these points on our graph. So for the x-intercept, we have negative 3.2. Negative 3.2 is simply negative 1.5. So we come to this here, which is going to be this point. As you can see, it is in between negative 1 and negative 2. Then we come to the next point, which is 0, 3. So at x equals 0, and then at y being what? 3. So we have these 2 points. You see, so this other point. The only thing we need to do now is to draw our straight line through. Now, the straight line we are drawing, is it going to be a dash, or is it just going to be a solid one? That is determined by the inequality symbol we have over here. So as we said, if it is less than or greater than, you use the dashed. You see, but then if it is greater than or equal to or less than or equal to, use the solid one. So all I'm going to do is you take your ruler, then you draw your straight line. You see, so it should pass through these 2 points. I'm going to extend this as well. This is my line, and mind you, we said it's supposed to be dashed. So I'm going to use these dash, as you can see over here. Now, after all this, we aren't done. We need to determine the region that actually satisfies our inequality. So we said you can pick the origin. So as you can see, the origin is within this region. Take note, the line we have drawn here has divided our Cartesian plane into 2 regions. So talking of these 2 regions, as you can see, I have differentiated them. This white region, that is the region below the line. This is our line over here, right? The colored straight line. And then the region above the what? The line, you see. So we actually want to determine which region satisfies our inequality. Is it the one below or the one above? And how do we do that? We said you pick any point at all, but it is easier with the origin. So testing with the origin, we know the coordinate of the origin is what? 0, 0. So we say testing 0, 0. Now, that simply means our x coordinate is 0 and our y coordinate is 0. So using our y is less than 2x plus 3, it means we have 0 being less than 2 into bracket 0 plus 3. That is substituting our x and y. We have 0, which is less than, we have a 0 plus 3. So you have 0, which is less than 3. Is this true? This is false. You see, so if this is false, then it simply means this region we have here, where we pick the 0, 0, you see where the 0, 0 is? It is in this region over here. It simply means this particular region doesn't satisfy the inequality. Hence, it is this region that actually satisfies. So you do your indication there. I'm just going to shade all that through. So this is going to be my region that satisfies what? My inequality. You can shade, you can use lines, whatever you want to do to indicate. Just make sure it is different from the region that doesn't satisfy. Now the question goes on to ask, you should determine whether 1, 5 is in this region that satisfies. Is it part of the region that satisfies? Let's actually locate 1, 5. To locate 1, 5, that is x is 1. So x is 1, then we move up to 5. This is the point over here. Now looking at the point, where do we have the point? You realize that it is right on our line. The point in question is right on the line. And if it is right on the line, because it is an inequality of this sign, we say it is not part of our solution. You see, it is not part of our solution because we don't have or equal to. If it was or equal to, then we can say any point on the line is part of the solution. But with dash lines, any point on the line is not part of the solution. You see, so with that, we are done with our solution. They say you describe how to graph this line. The description was done as we were doing all of this. First of all, you set your boundary line, and then you draw the boundary line. You do that by determining your x-intercept and y-intercept, which gives you 2 points to be able to draw your line. Now, the type of line is determined by the symbol you have here. So if it is less than or greater than, you use the dashes. If it is greater than or equal to or less than or equal to, use the solid line. And then you determine which of the regions actually satisfy your inequality. It is easier, you test with your origin, that is 0, 0. Then determining whether 1, 5 is in the region, it is no, because 1, 5 falls on our line, you see. And even on the other hand, we could have even test with the inequality. So it says y is what? 5. So 5 is less than, and then our x being 1. So that is 5 is less than, this gives us a 5. This is not true, you see. So even algebraically, it doesn't satisfy. So this is our first question. Let's solve a couple more questions just to enhance our understanding. I advise that as we proceed, you'd also take your graph book, then your notebook, and try as much as possible to solve along. As you practice, you get more understanding. So let's look at our second question we have here. It says we have to graph x plus y less than or equal to 6. We have to find the intercept for the boundary and test for 0, 0. So looking at our inequality, we have what? X then plus y is less than or equal to 6. So this is to imply that our boundary is going to be an equation. So x plus y is equal to 6. So with this, we would have to look for the x-intercept and the y-intercept. And we know at x-intercept, y equals 0. So at y equals 0, then we have x plus 0 equals 6. And then x is equal to 6. Also, at x equals 0, then we are going to get what? An x, which is 0 plus y is equal to 6. And then our y will be equal to 6. So the 2 points we have are now for the x-intercept, we have a 0. For the x-intercept, that is when y is 0, we have a 6, 0. And then for the y-intercept, we have a 0, 6. So these are the 2 points we need to locate on our graph to be able to what? Draw our straight line, which is our boundary. Now for the boundary, is it going to be a solid line or dashed line? It is going to be a solid, because looking at the sign we have here, it is all equal to, because of the presence of this equal to. That means all the points on that line also satisfies our inequality. So let's do that. So on our graph, let's identify our point. We have 6, 0. 6, 0 is going to be here. This is our 6, 0. Then on the y-axis, we have a 0, 6. So 0, 6 is also going to be right here. Then we draw a straight line through these 2 points. So drawing a straight line through these points, I'm just going to draw the straight line through it. See, so that is all. And then we extend the lines just to make sure it spans our graph sheet nicely. So by now you should know why we are using the solid lines and not the dashed. After drawing our line, we now want to test for the region that satisfies our inequality. So it is best we use the origin, you see, because the origin is 0, 0, and then it is easy to work with. So testing for what? 0, 0. That is, we have x plus y less than or equal to 6. Substituting our 0, 0, we have 0 plus 0 less than or equal to 6. 0 plus 0 gives us 0, and it is less than or equal to 6. That is true. And where do we have our 0? We have the 0 around here. So that is to say this region below the line we have drawn satisfies our inequality. So I'm coming to shade all of that. So this is going to be from all of this side all the way down here. Then it goes something like this. Now, as I said earlier on, you can use your lines to do it as well. So that is it for this particular question. We've been able to graph x plus y, which is less than or equal to 6. And we found the intercept for the boundaries, that is the x-intercept and the y-intercept, and we have tested for 0, 0 as well. With these two examples, I want to believe you've understood, and then you'll be able to do this very one. Hence, after reading the next question, I advise you pause and then try on your own before you look at the suggested solution. Our next question we have here says, graph 2x minus y greater than 4. Find the boundary intercepts, choose the correct line type, and determine which region to shade using a test point. This is very, very similar to all that we have done so far. So the inequality is 2x. We have 2x minus y is greater than 4. So to solve for this, we would first of all look for our boundary line. And we do that by determining at least 2 points using the equation 2x minus y is equal to what? 4. Now, for the intercept, we know at the x-intercept, y is equal to 0. So at y is equal to 0, it simply implies that we have 2x x minus 0, which is equal to 4. Making our x the subject, we have our 2x being equal to 4, which implies that our x is equal to 2. Hence, the set of points this is giving us what? 2, then 0. Then we come to x being 0. So at x equals 0, then it implies we have a 2 into bracket 0 minus the y, which is equal to 4. 2 times 0 gives us a 0, so you have 0 minus y, which is equal to 4. Making y the subject, we have our y, which is equal to a negative 4. Hence, the point this is giving us is 0, negative 4. So in our graph sheet, we simply locate this point. But right away, we can determine the region that is going to satisfy. So let's use 0, 0. So testing for 0, 0. That is to say, for 2x minus y, which is greater than 4. If you put 0, 0, are we going to satisfy this inequality? So we have 2 into bracket 0 minus 0 greater than 4. All this gives us 0, which is greater than what? 4. And we know that is not true. Hence, the region we have the 0, 0 is actually not going to satisfy our inequality. So let's go straight to the graph and then we draw a line and then determine our region. So we now come to our graph and then plot out our points so that we can draw our line through them. The first point is what? 2, 0. So we come all the way here, and as you can see, we have 2, 0. I've plotted that nicely over here. Then the next one is what? 0, negative 4. So we come to x equals 0, then y is negative 4. These are the 2 points that we have to draw our straight line through. So drawing our straight line, we look at the type of line we are supposed to draw. As you can see, it is greater than, it is not or equal to. Hence, we are going to use what? The dash. So all you are going to do is to take your ruler and then quickly draw your straight line through these points. So you make it as long as possible so that it becomes visible. So with this line drawn, all we want to do is to extend it also towards this side. Now we have our line. We want to determine the region. Per our calculation, we determined that the origin doesn't fall within the feasible region. As you can see, the 0 is not greater than 4. This is where we have our origin, and it is in the upper side of our line. Hence, we are going to shade this lower side since the upper side does not satisfy. See? So we then shade all of this over here, as I'll be doing very soon. So as you can see, I have shaded the feasible region nicely. Now, I do hope you were able to also do that yourself. Let's look at our next question. It will be a little bit different from what we did over here. Our next question here says, which of the following points lie on the region defined by y is greater than or equal to 3x minus 5? And the points are 2, 1, 0, negative 6, 3, 5. So how are we going to solve this type of question? There are 2 ways you can do this. Now, you can either use algebraic substitution or you can use the graph. Since we are working on the graph and we want to understand the graph further, let's choose the method of the graph. So looking at what we have, there is a y which is greater than or equal to, we have a 3x minus 5. This is our equation we were given. So if you want to plot it out, then we need the boundaries. So for the boundary, we are changing this to equation as we have done so far. So we have y is equal to 3x minus 5. So at x equals 0, we have our y, which is equal to 3 into bracket 0, then minus 5. That gives us a y equals what? 5. That is a negative 5. So it implies our coordinate is 0, negative 5. Then we come to at y equals 0. So at y equals 0, then we have 0 is equal to 3x minus 5. Making x the subject, we are going to get a 5 over 3. Now this 5 over 3 is simply a 1.6. So with that, the coordinate we are getting is x is 1.6 and then y is 0. So quickly go to our graph and then plot this out. But then before that, let's test for the 0. So testing for the origin. So the origin is what? 0, 0. So it simply implies that we have our y, which is greater than or equal to 3x minus 5. We have 0, which is greater than or equal to 3 into bracket 0 minus 5. We have all this giving us a negative 5. 0 is greater than or equal to negative 5. Remember, 0 is greater than all the negative numbers, right? So this is to tell us that our origin is within the range or the feasible region. Our origin, which is 0, 0, is within the feasible region. So let's see how we are going to represent it on the Cartesian plane. So on our Cartesian plane now, we identify our points and then try to draw our line. Now, we have our x-intercept being 1.60 and then the y-intercept being 0.5. So I'll identify my y-intercept here, which is 0, negative 5. And then we identify our x-intercept, which is 1.60. That is this point over here. Then we join these 2 points. So joining our points, I'm just going to take my ruler and join this straight line. You see, so we'll just end somewhere around here. And then you extend this as well downwards so that it covers your entire Cartesian plane. So with these, we are going to now shade the region. From our testing, we said the origin satisfies. You see, this is where we have the origin, and it is at this side of our line. You see, so we are going to shade all these regions and then say it satisfies. Okay, so let me quickly do that. So you see our region that satisfies. That is the region that has been shaded. Now back to the question. All we want to do is, if you're able to locate any of these points in the feasible region, then it simply means it satisfies. And there was one thing that we were to take note of. Our inequality here is y is greater than or equal to. Y is greater than or equal to. So that simply means the line we drew over here, this line, this particular line, wasn't supposed to be dotted, but rather is supposed to be a solid line. You see, so I've changed it to a solid line, then I'm putting it there. So you always take note of these. They are very, very important. I've now made it a solid line. Because if it is a solid line and then you actually put the dash, then you are trying to say that line is exclusive. It is not part of the solution, but that isn't the case. Any point on the line actually forms part of the feasible region. That is if it is greater than or equal to. With that said, let's look at our point. So the first one says 2, 1. The point is 2, 1. Where do you have our 2, 1? This is 2, and then 1 is also around here. We can plot that out and see. So as you can see, the 2 is up here, and then it joins toward 1. You see? Now that point you have there is on the straight line. And remember, this was why I emphasized that we needed to make it a solid line. If it is on the solid line, it simply means it is part of the feasible region. So yes, point A is part of the region defined by our inequality. Then we come to the next one, which is 0, -6. So 0, x is 0, then we come all the way to y being -6. This is the point over here. This is 0, -6. As you can see, it is not in the feasible region. So it is not in the feasible region, hence I'm going to let it be a red. The next point is 3, 5. 3, 5. So where do we have our 3, 5? There is 3 here, then we move up toward 5. So this is the point 3, 5. And as you can clearly see, it is within the feasible region because it lies in the region defined by our inequality. So that is just it. This is if you actually wanted to use the graph to demonstrate. But if you wanted to go straight forward, all you need to do is to do your substitution. So doing your substitution, what do I mean by that? So if you wanted to use the method of algebraic substitution, all we needed was, we know our y is greater than or equal to 3x minus 5. So it's just as we tested for the origin, we're going to do the same for all of them. And if it doesn't satisfy the inequality, it is simply out of the feasible region. So let's start with 2, 1. So testing for our first point, which was 2, 1, it simply means our y is what? 1, greater than or equal to 3 into bracket 2 minus 5. That gives us a 1, which is greater than or equal to, this is a 6 minus 5, which is 1. 1 is greater than or equal to 1. And that is this point we have over here. You realize that it was right on our boundary line. Hence, 2, 1 satisfies. You see, if we were to check for the next one, we have our y, which is -2. So we have -2 is greater than or equal to 3 into bracket 0, then minus 5. That gives us a -2, which is greater than or equal to, this gives us a -5. And is this inequality true? Is -2 greater than or equal to -5? That is no. So you realize that that fell outside our feasible region. You see, so this is how you can actually test if you didn't want to draw. You get it? So you could have drawn to illustrate by showing where the points are with respect to the feasible region, or you did the method of testing, so that if the inequality statement is false, then it simply means that particular point isn't in the feasible region. Linear inequality doesn't just solve these type of problems, but then it solves real life problems as well. It has to do with businesses, maximizing profits, and all that. Let's look at one of such a question, that is a word problem. So for our last question here, it says the school canteen can seat at most 50 people. Tables come in sizes of 4 seats and then 6 seats. Write an inequality, that is 1, 2, draw the boundary. 3, find 3 valid combinations of the tables. We have to write an inequality, we have to draw the boundaries, and then we have to find 3 valid combinations of the table. This is an example of a practical use of inequalities. So to illustrate what this question is actually talking about, you see, this is a table that can take just 4 students. That is because it's in a canteen, and this can take 6 of them. Now, the canteen is very big, but though it is big, it can take a limited number of students. That is 50 at most. So we want to use inequality to be able to determine how many of these tables can we arrange in the confined space. How many of the four tables, cum 6 tables, can we arrange all together? You see, that is what it is saying. So let me take this illustration away so that we start solving something. So writing our inequalities, looking at the information we have over here, it says a school canteen can take at most 50 people. The tables come in sizes of 4 seats. Now for the tables, we are using X. The number of tables cannot be negative. So that is the first inequality we can write out. So we can say X should always be greater than or equal to 0. And then the same applies for Y. So for Y as well, we would say Y should always be greater than or equal to what? 0. The X is for the 4-seater tables, and then the Y is for the 6-seater table. So with these two written, we now look at the capacity inequality. It says the school canteen can seat at most 50 people. So that is to say, for the X, table X, that takes 4-seater. If we add it to table Y, that also takes 6-seater. It should be at most. That is, it should either be equal to or less than 50. So these are going to be our three inequalities. We will call this our capacity inequality. With that, it is just the same procedure as we have always done. We have our equations, look for the boundary line, look for the feasibility region, and then you are good to go. So for this particular one, this is our y-axis, this is our x-axis. Hence, we just need to focus on this. So for our boundary, we have 4x plus 6y, which is equal to 50. We look for our intercept. So at x is equal to 0, we are going to get 4 times 0, which gives us a 0. So we have 6y is equal to 50. Hence our y is equal to 50 over 60, which gives us approximately an 8.3. Then we test for x. So at y equals 0, all of this is going to give us a 0. So that we have 4x being equal to 50. Making our x the subject, our x is equal to a 50 divided by 4. 50 divided by 4 gives us a 12.5. So with that, the 2 points we are going to plot are this one, which is a 12.50, and then the 0, 8.3. So let's go to our graph. But right before that, we can as well test for the feasible region with the 0, 0. So testing with our origin, that is 0, 0. We are testing it with this inequality, that is the capacity inequality. So we have 4 into bracket 0 plus 6 into bracket 0, which is less than or equal to 50. All these gives us 0. So 0 is less than or equal to 50. What is true? So this simply means where we have the origin, after drawing our boundary line, the region that has the origin is what satisfies our inequality, or it is representing the feasible region. So since we have done most of these already, I'm just going to plot it out as you see over here. This is the graphical representation of our inequality as we have. So for the 12.50, this is it over here, 12.50. And then we have the 0, 8.3. This is the 0, 8.3. Then we join our two lines. This is our origin. Now we realize that the origin represents the region that satisfies. So that is going to be here. So all of this region satisfied. But the question was, we have to find three valid combination of tables. Three valid combination of tables. Now, any coordinate at all over here is a valid combination. Any coordinate at all. But specifically, if you want the canteen to be full, then you are rather going to focus on the points that are on this line. And by so, I mean points such as 7, 2. So this is our 7, you see, and it links to what? 2. Then we have points also such as 5, 5. You see, so we have 5, 5 that touches the line. And then there is a 3, 8. And then finally, there is a 1, 11. You see, so these numbers you have here, if you remember, if you would remember, we said the X was for the 4-seaters and then the Y was for the 6-seaters. So these numbers we have here simply means if you have 2 of the 2-seaters, if you have 2 of the 4-seaters, and then 7 of the 6-seaters, you can actually fill up the canteen. If you have 5 of the 4-seaters and then 5 of the 6-seaters, you can also fill up the canteen. If you have 8 of the 4, 3 of the 6, you can also fill up. You see. Now, if you don't want it to be completely full, then you can take any of the points inside these shaded regions, and there are numerous of them. I should take note. You don't take decimal values. Take integer values, specifically positive integers, because we can't have a decimal number of tables. You see. So with that, you can take any of these values we see over here and it would work. You see. But if you want to maximize the space, then you would take what we have on the line over here. So that will be it for this session, and I do hope it was helpful. If there's any issue of concern, you can always let me know at the comment section. As usual, I'll leave you with some exercises so you try just to test your understanding. Here are just 5 that are based on what we've done on this lesson. If this is your first time and you think it will be of help to you, you can choose to subscribe if you so do, so that anytime I release a video, you'll be notified as well. Just have beyond numbers where we learn maths the easy way. Do stay safe and see you in our next lesson. Bye for now.